Hey everyone, and welcome to this explainer. Today, we're doing something really cool. We're going to explore the invisible electromagnetic architecture of the wireless world all around us. Seriously, we're decoding the actual language that engineers use to describe exactly how our cell phones, radios, and Wi-Fi routers talk to the universe. It's kind of mind-blowing when you really think about it.
And don't worry, we're not just going to sit here and read a dry engineering dictionary. We're going to build our understanding logically. Here's our agenda. First, the language of antennas. Second, the concept of polarization. Third, gain, power, and directivity. Fourth, navigating antenna fields. And finally, quirky antenna designs.
All right, let's jump right into Section 1, the language of antennas. Time to get our foundational vocabulary down tight.
So, our ultimate technical authority for this whole journey is the IEEE Standard 145, specifically the 1993 revision. This incredibly dense document is literally the gold standard. It represents a massive consensus of expertise, standardizing exactly what we mean when we talk about antenna tech. It's the rulebook, essentially.
Now, what actually is an antenna? The absolute baseline definition here is simply that part of a transmitting or receiving system that is designed to radiate or to receive electromagnetic waves. I just love how elegantly simple that core concept is. Before all the crazy math and physics kicks in, an antenna is really just the bridge between your physical device and the open air.
Just to quickly set the boundaries for our explainer today, the definitions in this standard assume that the antenna is a passive, linear, and reciprocal device. Now, reciprocal is a fantastic word here. It basically means that if a definition talks about the antenna transmitting, well, its use in a receiving situation is perfectly implied too. The physics work beautifully in both directions. It's a two-way street.
Moving on to Section 2, the concept of polarization. Fair warning, things are about to get very spatial and geometric. So the standard brilliantly breaks down polarization using something called progressive disclosure. It gives us three distinct but deeply related meanings, and it really helps to think about them in this exact order. First off, it applies to a field vector at a specific point in space. Second, we scale that up to describe a single frequency plane wave traveling through space. And finally, third, it applies to the antenna itself, specifically the polarization of the plane wave it radiates way out at large distances. Just picture the visual geometry of this for a second. Imagine the very tip or extremity of a field vector over time. As it moves, it traces out these distinct shapes, most often an ellipse. So the polarization of a field vector literally specifies the exact shape, the orientation, and the sense of this ellipse. It's basically the physical shape that the electromagnetic field is drawing in the air as time ticks forward. How cool is that? And this brings us to a really crucial definition: copolarization. This is defined simply as the polarization that the antenna is intended to radiate or receive. Think of this as the absolute optimal state. When your antenna is working perfectly, capturing the exact signal it was designed for, boom, you're operating in copolarization. But we have to contrast that immediately with cross-polarization. This is the polarization that's orthogonal, meaning at a right angle to that intended reference polarization. In the real world, cross-polarization usually means unwanted or just completely wasted energy. Like, if your antenna is trying to catch a vertical wave, but a bunch of energy is hitting it horizontally, yeah, that's cross-polarization. All right, Section 3, gain, power, and directivity. This is where we talk about focusing all that raw power. Let's ground these abstract ideas in some hardcore physics. Think about the number 376.730. This is the intrinsic impedance of free space, measured in ohms. It is an absolutely amazing constant of the universe. Whenever an electromagnetic wave travels through a vacuum, the ratio of the electric field to the magnetic field is always exactly this number. It's roughly 120 times pi. This single number sets the entire baseline for how radiation propagates through the void. Okay, now let's trace the journey of a signal. It's a bit of a process, but it maps out perfectly. Starting at the source, we have the raw power available from the generator. But as that signal moves forward, we hit reality. We encounter impedance mismatch factors, and we get down to the actual power accepted by the antenna. Then, factoring in radiation efficiency, we finally arrive at the actual power radiated. And that power is then shaped by directivity and gain to create the final radiation intensity. It's literally the complete life cycle of a transmission.
Let's clear up two terms from that journey. They get mixed up all the time: gain versus directivity. I always use a flashlight analogy for this. Directivity is all about the shape of the beam. How tightly are you focusing that light in a specific direction compared to, say, a bare light bulb shining everywhere? Gain, on the other hand, is the actual real-world output in that direction because it factors in the physical efficiency losses and the impedance mismatches of the flashlight itself. So directivity is the ideal shape, but gain is the messy, real-world reality.
Moving on to Section 4, Navigating Antenna Fields. Let's travel outward into space.
Let's see how the electromagnetic field actually builds spatially as we move away from the device. Right at the antenna surface, we're in the reactive near field, where energy is just stored rather than radiated. Take a step further out and we hit the radiating near field, also known as the Fresnel region. Here the wave is radiating, but the angular field distribution still completely depends on your exact distance from the antenna. Finally, keep going and we reach the far field, the Fraunhofer region. Out here the wave is fully formed and its pattern is essentially independent of how far away you get.
And finally, Section 5, Quirky Antenna Designs, because engineers are actually pretty funny with naming things.
First up, we've got the oddly named cheese antenna. According to the standard, this is a reflector antenna with a cylindrical reflector enclosed by two parallel conducting plates. But here is the absolutely crucial detail. Those parallel plates are spaced more than one wavelength apart. I guess someone looked at it and thought, yep, that looks exactly like a wheel of cheese cut in half.
Then we have the hoghorn antenna, and this one always gets me. It's defined as a reflector antenna consisting of a sectoral horn that physically intersects a parabolic cylinder. The really defining feature here is that part of one of the non-parallel sides of the horn is completely removed just to form the antenna's aperture. Next is the pillbox antenna. Now, if you remember the cheese antenna we literally just talked about, the pillbox is almost identical. It's that same cylindrical reflector enclosed by parallel plates. But the key difference? It's all about distance. In a pillbox, those plates are spaced less than one wavelength apart.
And to wrap up our quirky designs, we have the fishbone antenna. This is an end-fire traveling wave antenna. It uses a balanced transmission line coupled to an array of closely spaced coplanar dipoles. If you actually look at one from above, it genuinely looks just like a fish skeleton, with a long central spine and little ribs sticking out all along the sides.
So, we've gone from basic definitions to the wild geometry of polarization, navigated through electromagnetic fields, and even checked out some cheese and fish-shaped metal. Here's what I want you to think about. The next time you make a call or connect to Wi-Fi, ask yourself, what exact shape is the invisible wave connecting you to the world right at this very second? Is it linearly polarized? Circular? It is honestly mind-blowing to realize that highly structured, invisible physical waves governed by the exact rules we just talked about are passing right through you right now. Thanks so much for joining me on this explainer, and keep learning.
If you found this explainer helpful in grasping the complex and fascinating engineering, like, share, and subscribe to @MakersJunction on YouTube for more highly professional, basic to advanced engineering content. Keep exploring, keep building, and we'll see you in the next explainer.